So thanks. It's great to be here. I want to thank all of these organizations listed here for their tremendous support in bringing both a connection between human interests and science, and also OSHEP, the high energy physics community here in Australia, for helping to bring me here. And to Hugh Price especially, because he and Roger Penrose were the two people who really got me thinking about the arrow of time in a serious way, and thereby changing my life. And also, thanks to all of you for actually arriving here and thinking, just wanting to hear a lecture about this, especially because this morning I was doing a radio interview and we were taking questions from who knows where over the airwaves and over the text messages and so forth. And the final question we got was, "Oh, come on, isn't this all just tosh?" I thought that was very charming because that's not a word we would be using in the United States. But also, one of the lessons that I hope to get across to you here today is that even though you might not think about the origin of the universe and the arrow of time in your day-to-day lives, they affect your day-to-day lives in a very tangible way. I want to argue that it is things that were happening when the universe was created that very much has set the stage for things that are very familiar to you in your everyday life, going through the kitchen, just growing up and growing older, and all of that. So hopefully we'll connect these two ideas to each other and to other things you might be thinking about all the time. So I should set the stage by defining what I mean by time, and it gets a little bit confusing because, of course, words are not invented in any logical way. We have used the word time long before we had scientific understandings of what it meant. So really, I just want to distinguish between two different ways in which we use the word. And time, of course, helps us keep track of things changing through time. You quickly find there's just no way to define the word time without using it itself. But there's two different kinds of things that happen as a function of time. One is that things repeat themselves. A certain kind of thing happens over and over again in a repetitive, predictable way. And of course, other things don't repeat themselves. They change and they never change back. Both of these aspects are going to be crucial to understanding what we mean by time. Repetition is how we measure the flow of time, the passage of time. The fact that certain things happen and they happen over and over again, certain other things happen and they happen over and over again, and there's a synchronization between these things that happen. So way back, the first sort of knowledge of something like this is, of course, in ancient times, when we first kept track of time, we used astronomical clocks. We used what happened in the heavens to keep track of what time it was. You saw that the sun rose and the sun set, and it seemed that you had a feeling that it took about the same amount of time every day, up to the seasons changing and things like that. But then, how we would say it now is that the Earth rotates on its axis every time that it revolves, the Earth revolves around the sun every time it rotates around its axis 365.25 times. There's a predictable number of rotations of the Earth every year, every time we go around the sun once. And it's that reliability, the thing that something happens over and over again and something else happens over and over again the same number of times, that lets us measure time. So we have the Earth spinning on its axis. We have the pendulum of a clock oscillating back and forth once per second, and we have a little quartz crystal vibrating. Why are quartz watches especially good? Because the vibrations of a quartz crystal are especially predictable and reliable. Every second, this quartz crystal is going to oscillate the same number of times. It adds up to about 2.8 billion times per day. And you know that's going to happen. You know it's going to be the same number of vibrations between April 10th and April 11th as it is between April 11th and April 12th. When we have a watch, we know the minute hand goes around 12 times every time the hour hand goes around once. It's that repetition in synchrony that lets us tell what time it was. One simple way of defining time is it is what clocks measure. And clocks, of course, are just any example of this. Some things are not predictable. Some things you don't know when they're going to happen. But a clock is something when you know how many times it does something when other things are doing similar things themselves. So one example is, of course, in our bodies. We have biological clocks. We have slowly moving biological clocks and rapidly moving biological clocks. We have the beat of our heart. We have our breathing. We have electromagnetic pulses racing through our brain. If you have the feeling that time is moving more quickly or more slowly, that's because your biological clocks aren't always very good. Sometimes they start racing if you're excited or slowing down if you're bored, and then you feel that time is passing in a different way. One of the first examples of this is Galileo. We're celebrating the 400th anniversary of Galileo pointing his telescope at the heavens. when he was younger than that, when Galileo was a youngster in Pisa, he would go to church every Sunday, just like any good Pisan boy would. But he would get bored sometimes, and rather than listening to the sermon, he would look at the chandelier. And actually, I don't have any idea whether or not this story is true, but it's so good, I'm going to keep telling it anyway. It's one of those apocryphal stories that would be better true than checked out. So here is an actual photograph of the chandelier in the cathedral in Pisa, right next to the Leaning Tower. And what Galileo noticed is that sometimes he would go in there and it would be oscillating quite a bit. There had been a gust of wind or people had walked by and the chandelier was moving back and forth. Other times it was only moving a little bit. But it seemed, roughly speaking, that it would always take the same amount of time to go back and forth. Even if it had further to go, it would also move more quickly to make up for that, and the time it took between oscillations was about the same. So you or I would notice that. We might even not notice that, but if we did, we would go, ha, that's interesting, and then go back to thinking about something else. Galileo wanted to test it. So he starts using his pulse and compared the number of heartbeats to the number of oscillations of the chandelier. In fact, he found that it was true. The chandelier took the same amount of time, took the same number of heartbeats per oscillation, whether it was oscillating very far or only a short while. This was the first discovery that pendulums are good clocks. They are reliable. If you push them back and forth and just let them go, they click the same number of times for every individual kind of pendulum. It's the simplest way we have of telling time outside of the stars and the planets. But the other aspect of time that is also very interesting is that some things change with time. Some things do not go back where they started. Europe did not go back to where it started after World War I. If you notice that Poland changed quite a bit. It didn't exist, and there you go. Rock stars change quite a bit. Architectural styles change quite a bit. We all change quite a bit. In our lives, we are always born and then we die. And there is something about change that is not repetitive, that is a different aspect of time that we have to pay attention to. Some things not only change, but they change in irreversible ways. They change in one direction, but they never change back. So this is what is defining the arrow of time, the difference between the past and the future. If you took a movie of a pendulum swinging backwards and forwards, and then someone played that movie to you in reverse, you wouldn't be able to tell. It would look perfectly good moving forward in time or backward in time. It's that simple of a system. But if you took a picture of people aging or a cityscape changing, you would know if someone played it backwards in time. It would look weird to you. There's a directionality that time has that informs how we think about the way things change. And that's reflected in the universe itself. The past of the universe is very different from the future of the universe. We know that the past is very different from the current state of the universe. The universe is expanding. Everything is getting further apart from everything else. So in the past, things were closer together and the universe was more dense and also hotter. In fact, we think, we're not sure about this, but the smart money is betting that that expansion is going to go on forever. The universe is not going to recollapse. This is a discovery that is only about 11 years old now. It's part of the news story that he was mentioning to you. We thought for a long time that it was very sensible to imagine there was a big bang, the universe expanded and cooled off, but someday it would stop and recollapse into a big crunch. These days we don't think that. These days we think there was a big bang, everything was right on top of everything else. The universe has been expanding and cooling ever since, and it will continue to do so forever. That is a dramatic difference between the past and the future. As far as we can tell, the universe is not repetitive in any way. It's a once-in-a-lifetime thing. So what is going on here? What is the difference? What is it that makes the difference between these repetitive things that happen over and over again and these changes that can certainly define one direction? What physicists would do is define something called entropy. Entropy basically measures how disorderly a system is. And it first came into being in the scientific conversation in the early 19th century. And it's actually a very amusing story. Many of these great advances in physics were motivated by something other than absolutely lofty thoughts. In the case of entropy and the second law of thermodynamics, it was a French physicist and engineer, Saji Carnot, who was really upset that the British were building better steam engines than the French. So he tried to understand how steam engines worked, the sort of the basic principles behind them, and he ended up coming up with a law of nature that later got promoted, and we understood it better, into the second law of thermodynamics. That says that entropy, a measure of how messy a system is, always increases or stays the same in a closed system, in a system that you just leave by itself. So if you go into your office and you have papers stacked very nicely and neatly in a perfect order. That is low entropy. Things are orderly, things are arranged in a very delicate configuration. As time goes by, unless you tidy it up, those papers are going to become messier and messier until it looks like this. This is, does anyone know whose office this is? This is Alan Guth's office. Alan Guth is famous for two things. He invented the inflationary universe scenario of how the universe began, and he won a contest sponsored by the Boston Globe for the messiest office in the greater Boston metropolitan area. And it looks like it's about as maximum entropy as it can get, but every time you enter this office, it has a slightly higher entropy than it did before. So we feel this fact about change, that entropy tends to increase, that things naturally become messier. Things do not naturally clean themselves up. If you left this office alone and came back 100 years later, you would not find all of those papers stacked in nice, neat piles. Here is the classic example of entropy at work. We can take an egg and we can break it. We can scramble an egg. We can make an omelet. But no amount of work will help you make an omelet into an egg. And that is a universal truth as far as we can tell. Everywhere in the observable universe, everyone agrees that eggs turns into omelets. Omelets do not turn into eggs. We can imagine someday visiting a different planet around a different star where life was not based on carbon or something dramatic like that. No one imagines we will ever visit a planet on another star where omelets turn into eggs. This directionality of time, pointing from the past, low entropy, orderly, to the future, high entropy, disorderly, seems to be an ingrained feature of everything that we see in the universe around us. So we would like to understand why that is the case. You can just say that it is the case, and in fact, in the 19th century, what they would have said is that's a law of nature. That's separate from everything else in the early 19th century. But later, they learned that, in fact, you could derive the second law of thermodynamics from underlying principles. It's not a law all by itself. It can be understood in terms of more elementary conceptions. So here's one way of thinking about what the second law says. If you have a billiard table, and you have some billiard balls racked very nicely, and you take a cue ball and you smack it into the billiard balls, they will scatter around the table. That process, going from the orderly arrangement of billiard balls to the scattered arrangement, is perfectly natural. If I showed you a movie of it, it would make sense. But this process, going from a scattered arrangement of balls, if I hit that cue ball and it went into this nice orderly arrangement, you would be very surprised. That never happens. If I showed you a movie when it was happening, you would suspect I was just playing a regular movie backwards. You would not suspect I had actually given you a faithful representation of something that happened in nature. So this is one way of understanding. This is an example of the second law of thermodynamics in work. At work, you go from orderly, low entropy, to disorderly, high entropy. The other one never happens. But this is a case where we can try to understand what is going on in terms of the billiard ball dynamics. Physicists love billiard balls. They always assume there's no friction and there's perfect understanding of what's going on. We should be able to understand entropy in the second law by imagining billiard balls smacking into each other. The problem is, if you simplify all the way down to just two billiard balls, there is no arrow of time anymore. There can't be. If you have two billiard balls smacking into each other and going off some way, it is a feature of the deep down laws of physics that they don't see any arrow of time. I could play this movie backwards, I could have the inverse process, and it will look just as natural to you. And that's not just a feature of billiard balls, that's a feature of all of the laws of physics from Isaac Newton to Maxwell to Einstein to superstring theory. As far as we know, the deep down laws of physics are invariant forwards and backwards in time. That raises the mystery of why there is an arrow of time in the world around us. The fundamental laws of physics are perfectly reversible. They go backwards and forwards. Why is it that the world around us doesn't look like that? This reversibility of the deep down laws of physics is in flagrant contradiction to everything we see around us in the everyday world. So this was figured out, in fact, in the 1870s by Ludwig Boltzmann. This is Boltzmann's tombstone in Vienna, and he has an equation on his tombstone. So when I give this talk to physics audiences, I like to say, what is the equation that will be on your tombstone after you die? This is only his second most famous equation. I mean, they had multiple choice about what equations to put on Boltzmann's tombstone. So Boltzmann was the one, he didn't invent the idea of entropy, but he explained what entropy meant in terms of atoms. In the late 19th century, physicists were very unsure whether there were such thing as atoms. They were not at all convinced. Chemists were convinced that atoms existed, but there were plenty of physicists, especially in the German-speaking world, who doubted that atoms existed. And the way that physicists finally caught on was that realized that over and over again you could take some feature that you observed in the behavior of gases and you could explain it in terms of atoms. You can explain the temperature of a gas as the average energy of the atoms. You can explain the pressure of the gas as the atoms bouncing off the wall. Boltzmann says I can even understand the entropy of a gas or anything else in terms of the atoms that make it up. And his definition was simply, I can consider all of the arrangements of the atoms or whatever constituents make up some system, but I don't see those atoms. When I look at the gas in this room or any person on the street, I don't see every individual atom with its location and its velocity through space. I don't see all of the information I would need to use the laws of physics to say what's going to happen next. Instead, I see some macroscopic features. I see some observable things about this system that I'm looking at. So Boltzmann says that to every macroscopic configuration of a system, there might be many, many microscopic arrangements. So here's a picture. This is supposed to be cream and coffee, but I had to use coffee liqueur and white chocolate liqueur because it separates better. So this is a liquid version, a liquid alcoholic version of entropy, and you see that in this case, there's a separation between the white stuff and the dark stuff. And if you mix it, you will get a mixture, and that's a very natural thing to have happen. If I showed you a movie going from here to there, you would think that was natural. But I can stir this glass all I want. It is never going to go back that way. That's part of the arrow of time. The entropy has gone up from left to right. Boltzmann says that's because this is made of atoms, and I can tell the difference between the white chocolate atoms and the coffee atoms. So if I mingle different arrangements of the white chocolate without disturbing the coffee atoms, that's fine, but there are fewer ways to do that when there's this clean delineation between the different liquids than when they are mixed together. Here I can only mix stuff on the top with other stuff on the top, and vice versa with the bottom, but here I can mix anything with anything. So what Boltzmann says is that entropy just counts the number of ways we can arrange the atoms so that you wouldn't notice. You wouldn't be able to tell if I took the atoms in this glass of liquid and moved a couple of atoms around or reversed the momentum or the velocity of all those atoms. You just can't see that macroscopically. So Boltzmann says here is all the ways we can arrange something. Some are very obvious that they're in a delicate relationship, and those are low entropy. More of them are high entropy. There's more ways to be disordered. There's more ways to be arranged in a high entropy configuration. And if that's true, then it seems very natural that entropy goes up. There aren't that many ways to be low entropy. There are lots of ways to be high entropy. So if you start with a delicate configuration, it's just natural it will go into there, and it's very unnatural to go backwards. There are more ways to be high entropy than to be low entropy. And this picture, by the way, is dramatically unrepresentative of the real relative sizes of these arrangements. The high entropy region is enormously larger than the low entropy region. So really, you could stir this. Statistically speaking, Boltzmann says that if you stir this glass, and you wait long enough, eventually it will go back to that arrangement. The second law is not absolute, but you have to wait much, much longer than the age of the observable universe to get there. So for all intents and purposes, entropy only grows. It's not going to shrink. Now, people were very pleased with that, and in fact, it depended a lot on what country you were in. Sometimes we like to think that science is all about ideas. In fact, sometimes what your friends around you are thinking and their other commitments and so forth do matter. So the English loved Boltzmann's ideas, but his German and Austrian compatriots poo-pooed him, and he struggled all his life to try to get his ideas across. The nice thing is he explains why if you start with low entropy, you go to high entropy. But it clearly leaves a question to be answered. Why did the thing start low entropy? In this example, the reason why it started low entropy is because I stood there very, very delicately and I arranged it. Okay? Why does an egg turn into an omelet and not into an egg? Because entropy increases. But where did the egg come from? And the answer is it came from a chicken. And that chicken is not a closed system. That chicken has access to a low entropy surroundings around it. So there are explanations for these specific examples as to why you started low entropy. But what about the universe? Why is the whole entropy of the universe going up? It's easy using Boltzmann's ideas to predict that starting today, the entropy tomorrow will be higher. It's impossible, using only Boltzmann's ideas, to understand why the entropy was lower yesterday. Indeed, if you'd used only Boltzmann's techniques, since the microscopic laws of physics are time reversal invariant, you could prove the entropy was higher yesterday, just like you can prove it's going to be higher tomorrow. But that's not true. The reason is that there is something going on at early times. The reason why entropy of the universe, the disorderliness of the universe, was lower yesterday than it is today is because it was even lower the day before that. And the reason why the entropy was even lower the day before that is because it was even lower the day before that. And this logic goes all the way back to the beginning of the universe. The reason why in our kitchens we have eggs that we can turn into omelets is because the Big Bang had a low entropy. And you're laughing, I hear you laughing, but it's the truth. We are embedded in a larger system, and this is being reflected in our everyday lives, and this leaves us with a mystery. Why did the universe have such a low entropy when it started? So to think about that a little bit, here's a picture of the universe. This is Edwin Hubble. He's looking a little smug, and as well he should. Edwin Hubble discovered the two most important facts about the universe. Number one, it's big, and number two, it's getting bigger. Now you might say, probably someone had guessed that the universe was big even before Edwin Hubble came along. But here is a picture, you can't see it because it's a little bright in here, but here's a picture from the Hubble Space Telescope, named after Hubble. This is the picture that you get if you take a really, really precise telescope up above the atmosphere of the Earth and you point it at an empty region of the sky. Sky was a region where, as far as you know, there's nothing there. And you just let it sit there collecting light for hours and hours and hours. And what you see are all these little blobs. They're very faint, but there's some of them that are quite a bit brighter, and astronomers 100 years ago certainly knew that they were there. They were annoyances because when you were looking for comets, you kept getting confused because you used to see these little blobs. What were they? And there was a debate that was going on. Some people thought that they were just a cloud of gas here within our galaxy. They knew that there was something called our galaxy, the Milky Way, the collection of stars, 100 billion stars we now know, that orbit around each other. So they thought that, well, maybe these are just clouds of gas within our galaxy. Other people thought maybe they're separate galaxies. Maybe everything that we see here is a galaxy just like our own, a collection of its own 100 billion stars. And it was Hubble who answered that question. He showed that things like this beautiful spiral, really is a galaxy similar in size to our own. There are 100 billion stars in that galaxy, and there are 100 billion such galaxies in the observable universe. So the universe is getting big. Hubble also showed that it's getting bigger as time goes on. The universe is today pretty darn big, tens of billions of light years across, but you can trace it back. It's expanding right now, which means the different galaxies are moving apart from each other. It does not mean the things that are held together are expanding. So galaxies themselves do not expand. Galaxies that are far apart are expanding because the space in between them is growing. But an individual galaxy is held together by the force of gravity, so it is not expanding with time. Atoms are not expanding with time. You are not expanding with time. Or if you are expanding with time, it is not because of the expansion of the universe. There are other answers. But given that the universe is expanding right now, we can play that movie backwards in our minds, and we can say, where did it come from? 14 billion years ago, if you extrapolate backwards using the known laws of physics, everything was on top of everything else. We call that moment the Big Bang. You will hear certain cosmologists talk about the Big Bang as if we know something about it, but we don't. We actually know with very good precision and reliability what the universe was like 1 second after the Big Bang. But that first second is still a complete mystery, and the first 0 seconds is an absolute mystery. We have to keep an open mind about what is going on. As the universe expands, it becomes more dilute, things stretch apart, and photons, the particles of radiation, go from being short wavelength and high energy to long wavelength and low energy. They lose energy, the universe cools off as a function of time. So the future of the universe is that it's going to be increasingly empty, desolate, and cold. That's just what science tells us. We can't really do anything about it. The third important fact about the universe, remember, number one, it was big. Number two, it's getting bigger. Number three, it's getting bigger faster. This was discovered in 1998. There were two groups, including one led by Brian Schmidt here at Mount Stromlo Observatory in Australia, that used supernovae, bright exploding stars, to measure the change in the rate at which the universe is expanding over time. They were really thinking that they were going to find that it was slowing down. That just makes sense. If the universe is expanding, there's everything in the universe pulling on everything else. You'd expect that expansion to slow down as a function of time. Instead, what they found is that the universe is accelerating. As things move apart in recent billion years, the universe has started moving apart even faster. If you looked at a galaxy and you took its velocity right now, and you came back a billion years later and took its velocity again, it would be higher when you came back later than it was the first time. Why is this happening? We're not absolutely sure, but we have ideas. We have one very good idea called dark energy. It's simply the idea that empty space has energy, that if you took a little cubic centimeter of space and removed all the stuff, removed all the light, all the matter, all the energy that you could possibly remove from it so it was empty, and you said, how much energy is there in that empty cubic centimeter of space? Einstein tells us that there's no reason for the answer to be zero. The answer is some constant of nature, some number, the intrinsic energy in space itself, sometimes called the vacuum energy or the cosmological constant. Here's a picture that I took of it, but this is a false color picture. It's really black. It's empty space. It's about 10 to the minus 8th ergs per cubic centimeter, if our theories are right. And what that means is, Einstein also told us that energy helps make the universe expand. It's the amount of energy in the universe that determines how fast it's expanding. At early times, when the universe had a lot of energy in it, it was expanding very fast. You would have expected as it dilutes away, the expansion slows down. But in fact, this dark energy does not dilute away. It remains 10 to the minus 8th ergs per cubic centimeter, even as space grows. So it builds up. In between you and a galaxy, there's a certain amount of dark energy. But as that galaxy moves further away, there's more and more dark energy. You see the galaxy move away faster and faster. And if that's true, and it remains that way, which is the most likely possibility, but certainly not set in stone, another thing we should keep an open mind about, but the simple idea is that this vacuum energy never goes away. The universe expands, it cools off, faster and faster, and pretty soon, cosmologically speaking, we're going to be in an empty, forbidding, lonely universe. So that's the universe. I'm sorry to, be such a downer about it, but we have a few billion years to go before things get completely empty. So we can tell this story in terms of entropy. We can ask, how does the evolution of the universe relate to the arrow of time that we observe when we break an egg and make scrambled eggs? Well, at early times, the universe was very smooth. We see today in the universe, we see galaxies, we see clusters of galaxies, stars, planets, etc. It's a lumpy universe on small scales. But if we look at sufficiently large scales, if we average out over billions of light years, it begins to look very smooth. And that's because at early times, the universe was extremely smooth at all scales. And it's only on small scales that we've had time to go from this smooth universe to have gravity pull things together and make stars and galaxies. So this is a low entropy configuration. As the universe expands, gravity pulls things together, the contrast knob is turned up on the universe, and the entropy goes up. Now, the entropy is going to continue to go up. That's the second law of thermodynamics. That's going to happen. So in the future, what's going to happen? Everything empties out. So we go from smoothness to lumpiness, and we're going to go back to smoothness again. There's no direct, simple relationship between smoothness and lumpiness and entropy. What there is the fact that this configuration of stuff in the early universe, there was a lot of stuff. And it was all in one very, very delicate arrangement, so there's the same amount of stuff everywhere. That's a very specific arrangement for the early universe to be in. It has a low entropy, and that entropy increases as you make structure in the universe, and that is reflected in the world we see around us every day.